Hey everyone, my name is Bo. I'm a final year PhD student at the University of Toronto. I'm very excited to be here to share with you our paper on using machine learning to solve very large bi-level programs. This method was motivated by a real application in bicycle infrastructure planning. We all know that cycling has become increasingly popular in recent years because it's healthy, sustainable, and good for the environment. However, lots of people still choose not to bike because cycling can also be very stressful, especially on road segments with heavy car traffic. To make biking safer and more inviting, the City of Toronto is looking to build over 100 kilometers of new bike lanes from 2022 to 2024. Although this is perhaps the most ambitious plan in the city's history, 100 kilometers is still relatively small compared to the huge road network we have in Toronto. This raises a very natural question, which is then, where should we build these new bike lanes? To answer this question, in collaboration with the City of Toronto, we formulated a bi-level optimization problem to identify the best locations for new bike lanes. In this model, a transportation planner first selects the locations of new bike lanes denoted by X. Next, using the road network designed by the transportation planner, a large number of cyclists bike from their origins to their destinations. The goal of the transportation planner is to maximize the total utility of all the cyclists, which depends on the route taken by the cyclist. This utility function has been shown to be highly correlated with the cycling mode choice in Toronto, so by maximizing the total utility, hopefully we can encourage more people to bike in the city. This optimization problem turns out to be very, very difficult to solve because we want to consider over 1 million cyclists in Toronto, corresponding to over 1 million followers in this bi-level formulation. The optimization problem was so large that we couldn't solve it with any existing methods. To tackle this challenge, we propose a new machine learning augmented optimization model to approximate the huge bi-level program we just formulated. First, to improve the computational tractability, we sample a small number of cyclists and model their routing problems explicitly, so we know the exact utilities for them. Next, using this cyclist as the training data, we train a machine learning model that predicts the cyclist utility based on some cyclist features. Once we have this model, for example, a linear regression model, we plug this model into the objective function to approximate the utility of other followers based on their features, but without solving the routing problems for them. Since the utility depends on the locations of new bike lanes, which may change during the optimization process, we need to synchronize our machine learning model weights W and the locations of new bike lanes X, so we can dynamically adjust our prediction to reflect the real impacts of these new bike lanes. To make this possible, we first include all the machine learning model weights as decision variables in this formulation. As a result, we can simultaneously optimize the locations of new bike lanes and retrain this machine learning model accordingly. To build a connection between these two sets of decisions, we add a constraint that under any bike lane designs, we should always adjust our machine learning model accordingly, so the training loss is always upper bounded by a constant. This simultaneous machine learning model training and optimization framework represents a new paradigm of integrating these two wonderful methodologies. The resulting optimization problem is tractable because we only explicitly consider a small number of routing problems, but this model can still generate high-quality decisions to the original bi-level model because the machine learning approximation helps us to capture the bigger picture. Indeed, through theoretical analysis, we demonstrate that under very mild technical assumptions, the bike lane design from our optimization problem achieve an upper bounded optimality gap on the original model, which considers all the cyclists in Toronto. We perform extensive numerical experiments to demonstrate the strong performance of our method. In particular, in the planning horizon from 2022 to 2024, our method can match the performance of the current infrastructure planning practice while reducing the bike lengths by 25 kilometers. This reduction corresponds to a cost saving of over 18 million Canadian dollars. In summary, in this paper motivated by a real application, we propose a machine learning-based method to solve bi-level programs with a large number of followers. We also propose many algorithms to enhance the performance of our model. All the methodologies proposed in this paper are very general, so they are also applicable to many other problems beyond bicycle infrastructure planning. Because of the strong performance, we're currently using this approach to support Toronto's 2025 to 2030 bike infrastructure planning. We're also actively talking with practitioners in other cities, hoping to apply our method to make biking safer and more inviting in many other places.